This is a continuation from part 2, where the expansion of square of a sum or difference of a binomial was discussed, along with the factorization of a difference of squares. The latter was extended to include numbers which are not perfect squares. The difference of squares was extended to include sum of squares resulting in the use of imaginary and complex numbers. The factorization of difference of squares was extended to factorize quadratic trinomials, which is the focus of the question raised, called the completion of squares. Consider the examples given in the original question, namely the factorization of the following using the completion of squares. Not all the steps are given as this was discussed previously. X squared plus 5x plus 4 is equal to x plus 4 into x plus 1. X squared plus 8x plus 14 is equal to x plus 4 plus root 2 into x plus 4 minus root 2. X squared plus 6x plus 18 is equal to x plus 3 plus 3i into x plus 3 minus 3i. Let us compare these quadratics with its general form x squared plus kx plus l. Please study the table below. The quadratics are listed in the first column. Therefore, the corresponding values of k and l of the general form of the quadratic is given in the second and third columns. As per the derivations shown previously, the corresponding values of p and q are shown in the next two columns. In the last two columns, the computation of the sum of p and q and as well as the product of p and q are shown. It is clear that in all instances, p plus q is equal to k and p times q is equal to l. I know that the arithmetic operations of radicals and complex numbers are advanced to those who are seeking an answer to the question raised. It is now clear that in factorizing the following quadratics, x squared plus 5x plus 4, the required numbers are ordinary integers 4 and 1. X squared plus 8x plus 14, the numbers required are not ordinary integers. X squared plus 6x plus 18, the numbers required are not ordinary integers. Therefore, the latter quadratics could not be factorized because we are looking for ordinary integers that would satisfy the sum and product requirements. Although I have now answered your original question, I must now answer your question that arose right now. Namely, how can one find out whether a quadratic can be factorized using the usual practice? Let me answer your question as follows. The general form of the quadratic is x squared plus kx plus l. Let us now use the technique of completing the square. As was demonstrated earlier, the coefficient of the x term of the quadratic is halved and the square of the same is added and subtracted to maintain the equality. Terms are now arranged to obtain a difference of squares, namely x plus k by 2 whole thing squared minus the square of square root of k squared minus 4l divided by 2. The foregoing derivation is reproduced for now for clarity. Now concentrate on the quantity k squared minus 4l. It can be one of the following. It is a negative number which follows that the numbers for p and q are imaginary quantities. The remaining choice is that either it is a positive number or zero, and that can be categorized into two possibilities, either being a perfect square, in which case the whole numbers can be found as usual to factorize, or the numbers is not a perfect square, which follows that the numbers for p and q are radicals. The conclusion is test whether k squared minus 4l is a perfect square or not before trying to factorize in determining the two numbers. Problem. Even if two numbers exist that satisfy the sum and product criteria, it is not discovered by oversight. Example. Factorization of x squared plus 25x plus 144. If we check for k squared minus 4l, it is equal to 625 minus 4 times 144, and that is equal to 625 minus 576, which is equal to 49, and is a perfect square. Now we determine the factors of 144, such as 144 is equal to 1 times 144, or 2 times 72, or 3 times 48, or 4 times 36, etc. But by oversight, we miss the pair of factors 144 is equal to 16 times 9. Hence, the conclusion of the inability to factorize. To overcome this problem is to factorize through completion of squares. Its demonstration is as shown, but will not describe in detail as the technique was described many times over. And finally, the answer is x plus 16 into x plus 9. In the foregoing example, the calculations involved in completion of squares appears to be long-winded. We know that the factors of x squared plus kx plus l are x plus p into x plus q, where p plus q is equal to k and pq is equal to l. We define the two quantities A and D such that A is equal to P plus Q divided by 2 and D is equal to P minus Q divided by 2. Therefore, A squared minus D squared is equal to P plus Q divided by 2 whole thing squared minus P minus Q divided by 2 whole thing squared, which ultimately is simplified into PQ. It follows that P plus Q is equal to 2A equals K and PQ is equal to A squared minus D squared is equal to L. Therefore, the general form of the quadratic can now be written as x squared plus 2ax plus A squared minus D squared. The problem highlighted was, by oversight, we missed the required factors of the last monomial number, such that its sum is the coefficient of the x term. Making use of the general form x squared plus 2ax plus a squared minus d squared, we commenced our operations with the coefficient of the x term. Applying it to the given example x squared plus 25x plus 144, 2a is equal to 25, which follows that a equals 25 by 2. Hence, a squared minus d squared is equal to 144 and d squared is equal to 49 by 4 after simplification, which follows that d is equal to 7 by 2. Therefore, p is equal to a plus d, which is equal to 16, and q is equal to a minus d equals 9. Hence, x squared plus 25x plus 144 is equal to x plus 16 into x plus 9. It is important to know what you are in for. Given the quadratic x squared plus kx plus l, compute the value of k squared minus 4l. As stated before, depending on its value, a number can be found for p and q, or it cannot be found for other reasons, as shown. In problems given at juniors level, the quantities should be a perfect square. If not, one can confidently state that it is not factorizable. Clearly, in this instance, there should be two numbers such that their sum is k and their product is L. It could not be found due to confusion. That's the only conclusion if it is not found. Having computed k squared minus 4l and determined that the quantity is factorizable, identify whether the quadratic is a square of either a sum or difference of algebraic expressions, in which case k squared minus 4l is equal to 0. Then find out whether it is a difference of two squares, in which case k is equal to 0 and l is a negative perfect square. Finding two numbers such that their sum and product are known numbers, such as x squared plus 80x plus 1200. Since the sum of 20 and 60 are 80 and the product is 1200, x squared plus 80x plus 1200 is equal to x plus 16 to x plus 20. The other technique is completing the square, which is already described, and we get the same factors. Then the semi-sum and difference method can be applied to find the same factors as shown. If necessary, pause the video. Note that having established that it is factorizable, don't waste time going in circles. If you cannot spot two numbers satisfying the sum and product required, use either semi-sum and difference method or completing the square. Example: x squared plus 98x minus 200. The k squared minus 4l value is equal to 98 squared minus 4 times minus 200, which is equal to 10,404, and which in turn is equal to 102 squared. The ability for quick mental computation is a good asset, which most of us may not have. If I spotted that 100 plus minus 2 is equal to 98 and 100 into minus 2 is minus 200, then x squared plus 98x minus 200 is equal to x plus 100 into x minus 2. If I did not spot the numbers, use, say, completing the square, in which case x squared plus 98x minus 200 is equal to x plus 49 plus 51 into x plus 49 minus 51, which is equal to x plus 100 into x minus 2. Applications. Question: factorize the following trinomials: x squared minus x minus 12 and x squared plus x minus 12. The calculation of k squared minus 4l, in both the instances, we obtain a perfect square. Well-known sum and product method would yield x squared minus x minus 12 is equal to x minus 4 into x plus 3, and x squared plus x minus 12 is equal to x plus 4 into x minus 3. The completing of square method will also give x squared minus x minus 12 is equal to x minus 4 into x plus 3. Continuing with the completion of squares, factors of x squared plus x minus 12 is again obtained as x plus 4 into x minus 3. Sum and difference method is also illustrated here, but carefully observe how calculation is done. If necessary, pause the video. All this time, the discussion was around quadratics where the coefficient of the square term was 1. What about the following examples? 1. 3x squared plus 31x plus 80. 2. 6x squared minus x minus 117. The answer is that in the question you raised so far were all regarding quadratic expressions where the coefficient of the square term was 1. Having discussed about it, now it is easier to discuss about quadratics where the coefficient of the square term is not 1. However, that must be examined in a different part. This is the end of part 3. In this part, we answered the question as to why certain quadratics could not be factorized in determining two rational numbers satisfying the sum and product conditions. An outline was given as to how to commence the process of factorization. We never discussed about quadratics of which the coefficient of the square term is not unity, which we would be discussing in the next and concluding part.